I'm Brooke.
And I'm Megan.
And we did our topic on calculus on the farm. So. Oh. Welcome to the... Alrighty, so the reason we chose our topic is because you can basically drive down almost any road in Minnesota in our area and see either a field or a farm, or you see a tractor sitting on the side of the road or something. So obviously it's pretty key to central Minnesota living to have farms around. And then all three of us have had parents that had backgrounds in the farm, so all of our dads grew up on family farms when they were kids. So we've all kind of heard the stories and we're all kind of interested in that. And then Megan is obviously still connected to her family farm, and she works on it like at least once a week. She's milking cows or helping out over there. And so as she looked around, she kind of saw all the buildings and all the different technologies there, and she realized that there was a lot of different mathematics like behind the farm, and so we started to see calc problems within it too. So we decided that we could easily kind of find a way to make this work for calc.
Okay, so a little bit of history of farming. In 8500 BC, people started to grow wheat, barley, and peas. Not until 7000 BC is when they started to domesticate animals such as sheep, pigs, and goats. In 6000 BC, they started to domesticate cattle. And then in 900 AD, some type of heavy plow was invented to help them with the farming and on the fields. And the Aztecs grew some maize or corn, and then Incas grew potatoes, peppers, and tomatoes. And the picture shows an Aztec harvesting some corn.
So this is like history on our farm, particularly our farm. And so my grandparents purchased the farm in 1944, or my great-grandparents did that, and then my grandparents took over in 1960. They went from a tie stall parlor into a tandem parlor, which has 4 cows on each side, and that makes milking more efficient and faster and allows you to have more cows to milk too. And that was in 1994, or 1972. And then in 1994, my uncle and dad formed a partnership and took over the farm for my grandparents. In 2004, they added on to the milking barn, so that way they could increase the herd size from 80 to 110 cows. This made more stalls, so the cows could lay down more, and then it helped with the overcrowding in the barn. And also we had recently added an automatic calf feeder, and so what that does, it puts the right amount of milk replacer that it needs in the water, and then the calves can go up there like 6 times a day, depending on what they get. They have a chip in their ear that tells the calf feeder what to give them, how much to give them, and if they can get some, because sometimes they can't get it whenever they want. It's set on a certain time period. And it also helps the calves grow healthier and more, like, better growth, I guess. They also added a heifer facility, and what that did is has 5 pens with headlocks in there, and that helped with overcrowding from inside of a barn that we have, so now they can go outside too. That was in 2012, and the farm continues to grow to this day still.
Alright, so for our first problem, we found that cow number 12 is milked in 7 minutes. And so on the farm at the Ackermans, the amount of milk is like how much you get is measured in pounds. So like when you go to the grocery store, you buy a gallon of milk. But on the farm, it's measured in pounds. And we took increments at every minute of how much milk was produced, like the total amount. And so we want to find the average rate of milk produced from time 0 to time 7 minutes. And so we just took f of 7 minus f of 0 over 7 minus 0, which is your total time. So then you got 49 minus 0 over 7, so you got about 7 pounds of milk per minute from cow 12. And then we also wanted to find the rate of milk extracted at times that we didn't take intervals on, and so or data on. So at time t equals 2.5, we just did the 2 areas that were closest, so obviously 2.5 is in between 3 and 2. And so we did 31 minus 19 over 1 minute, and we got about 12 pounds per minute there. And then we decided we wanted to do at 4.52 just to kind of compare as we got farther along. Was the cow producing more? Was it producing less? And we saw that at time t equals 4.5, the cow produced about 6 pounds of milk per minute. So it just kind of shows that as time went on, the cow was like extracting less and less milk. And then we wanted to find the average amount of milk from time 0 to 7 minutes. So we did the integral of the function, and so we just added all of our amounts together and then divided it by our total time and got about 34.571 pounds of milk. And then just a little bit of history on the average rate and amount. We found that Leibniz and Newton in the 17th century kind of just threw it out there and found the difference in like the derivatives and the integrals, and so obviously those are really important to the rates because like the derivative is just like an instantaneous rate. And then the average amount, since they kind of were crowned for derivatives and integrals, we can thank them for the average amounts. And then at this time, we wanted to kind of see if you guys were paying attention. And we've kind of had something that popped up quite often. And so keep an eye out for it. It's going to keep popping up. Kind of keep total from this slide on. And then we have a prize for whoever gets the closest amount to it.
Alright, so we also did Riemann sums for a math problem, and what we did is we took our metal barn that's in this shape, and we took 9 points in there, and I measured what each point was at. So if we had 9 points and the barn was 40 feet, we had 5 feet intervals, or 45 feet I think it was. And so the hay bales were all the way to the top, so I could measure on the hay bales at what point it was. And the barn was 25 feet tall at the tallest, so then we did trapezoidal Riemann sums, and that would be base 1 plus base 2 times 5 divided by 2. So then to do this, we just added them up at each point, and then also with the 17 feet 1 inch, we couldn't like add that up, so we had to convert the inches into feet. So we took like 1 divided by 12, or 5.5 divided by 12. And so we got like 17.083 times 5 divided by 2. And after all that was added up, we got 742.08 square feet for the total area of this barn here. And then we also did right and left Riemann sums to see how they compared. And they both ended up being 742.08. And we were like, oh, that's kind of weird. And so the barn is actually perfectly symmetrical. And so each underestimate on this side became an overestimate on this side, so they evened out, and then it didn't matter which side we started on. Some history, it was created by Bernard Riemann. He went to the University of Göttingen in 1846, and then he broke away from the 2D mathematics. He also had the Riemann hypothesis, which was discovered in 1859, and he was famous for unsolved problems in mathematics.
Okay, so now we are going to plant some corn. One row on Megan's field is about a half mile long. So as we start planting corn, our speed is 0 miles per hour. At the end of the row, our speed is 16 miles per hour. So this graph just shows like our travel along one row of the field. So we have distance or miles on the y-axis and time in minutes on the x-axis. So we're going to find the instantaneous rate of the tractor. So since our path is continuous, it has to be differentiable. So there must be a number c in 0 to 1/2, such that f of b minus f of a over b minus a is equal to f prime of c. So we took f of 3 minus f of 0 miles over 3 minus 0 minutes. So that equals 1/2 miles over 3 minutes, which is equal to 1 mile for every 6 minutes. So therefore we are going an average of 1 mile for every 6 minutes by the mean value here. Okay, so if we are going an average of 1 mile per every 6 minutes, we're going to find our average miles per hour. So we can find our average miles per hour by using the secant line. So we took our values of our 1/2 mile that we traveled in 3 minutes. So we did 1/2 mile over 3 minutes times the 60 minutes over 1 hour. So because we're changing the units, so we wanted to get it to miles per hour. So we got an average of 10 miles per hour on our one pass down the field. Okay, so how long will it take to plant all of the corn in Megan's field? So Megan has a tractor that can plant 6 rows of corn at a time, and each pass one way takes about 3 minutes, as we said before. So if we can plant 400 rows of corn, we have to divide that by our 6-row planter to find out how many passes we can get on the field, which is about 66.667 passes. So if we take that number times our 3 minutes that it took for each pass one way down the field, it would be about 200 minutes, which is 3 hours and 20 minutes. So a little bit of history on instantaneous rate. It was discovered by Newton and Leibniz because they discovered like velocity and the derivative. So the derivative tells us the rate of change of one quantity compared to another at a particular instant or point. So that just gives us how we find instantaneous rate. Okay, since the cows are eating the corn that we just produced, manure is constantly produced at a rate proportional to the amount of manure left in the pen. So this is shown as the derivative function of dy dt equals ky, where y is the amount of manure left in the pen at any time t. So to start, there are 350,000 gallons of manure in the pen. This is the maximum amount of manure in the pen before it would start to overflow.
That's how big the pit is too. That's how big our pit is underneath the cow barn.
Okay. So then 2 years later, there were 175,000 gallons of manure remaining. But it will no longer be efficient to take manure out of the pen if there are 20,000 gallons. So we're going to find the equation for y, the amount of manure remaining at any time t, and we're also going to find the rate, the amount of manure in the pen is decreasing when there are 250,000 gallons of manure remaining. And in order to be efficient, we're going to find the time t that manure should no longer be taken out of the pen. So, A, to find our y equation, we have our given information, which is dy dt equals ky. We are going to use separation of variables to figure out y. So we're going to do the integral of 1 over y dy equals the integral of k dt. So when we take the antiderivative of both sides, we're going to get the natural log of y equals kt plus c. So when we solve for y, it's going to be y equals c e to the kt. We have an initial amount of 350,000 gallons of manure, so we're going to put that value in for c. So y would equal 350,000 e to the kt. And we are also given that 2 years later, there are 175,000 gallons remaining. So we'll put 175,000 in for y and put the 2 in for t because there's 2 years. So then when we divide the 350,000 by the 175,000, we get 0.5 equals e to the 2k. So we're going to take the natural log of both sides. So the natural log of 1/2 is equal to 2k to the natural log of e. The natural log of e equals 1, so we're just going to divide the natural log of 0.5 divided by 2. So we get k is about negative 0.347. So we plug our k value in there, so y is equal to 350,000 e to the negative 0.347 t. So B, we're going to find how much the manure is decreasing when there are 250,000 gallons remaining. So because that is a rate, we use the derivative formula. So we do dy dt is equal to 250,000 k. So we just found our k, so we just plug that right up in there, and we get about negative 86,643.398 gallons per year. So when there are 250,000 gallons of manure remaining, we're taking out about 86,000 gallons. And then part C is when it's no longer going to be efficient to find how much the manure is going to be taken out. So 20,000 is equal to 350,000 e to the negative 0.347 t. So when we take 20,000 divided by 350,000, we get a simplified fraction of 2 over 35, which is equal to e to the negative 0.347 t. So we're going to take the natural log of both sides. So when we do that, the natural log of e equals 1, so we're going to divide by negative 0.347. So the natural log of 2 over 35 divided by negative 0.347 is going to be our time t. So we get a value of about, so T is equal to about 8.248 years that it will no longer be efficient to take manure out of the pen. So some history of integrals and natural logs. So the history of integrals first. Cavalieri discovered the integral in 1635. He was an Italian mathematician who used indivisibles as his theorem to find integrals. Indivisibles are like infinite number of points on the curve. And then the history of natural logs. Euler discovered the natural log, but he used the notation L and then X. So there was no N when Euler initially wrote it. Stringham was the one who put the N in the natural log. So in 1893, that is when he put the N in the natural log in his book Uniplanar Algebra.
Alright, so this is just going to kind of show you a little bit of what our next problem kind of talks about. So we have elevators that will bring we have elevators that will bring the hay bales and haystacks up into the top of the barn where they want them. So just kind of plop it on there and it does work fine. So just kind of shows you. Just because I didn't know what it was personally, because like my family farm that I used to go to when I was a kid, we never like saw any of that happening. So Megan kind of had a hard time explaining it to us, so we decided if we couldn't explain it, we should probably show you guys a video as well. Alrighty, so we want to get the hay bales to the top of the stack, so we need to obviously set the elevator at the right angle of elevation. And so this is our theta, I guess you could call it, or our x, and we realized that it was just tangent because it was opposite over adjacent, and so we did the tangent of x equals 20 over 17, so we just did the arc tangent of both sides, and we got x equaling the arc tangent of 20 over 17, and so we discovered that in order to get our hay bales to the top of our barn where we wanted them, we needed our angle set at 49.635 degrees. And then kind of the history of like trig, the Babylonians in 300 BC kind of used it to make angle measurements within like their housing and their daily lives. And then Hippocrates in the 12 book work on chords in a circle. And so he did the trig within like circles and putting them on the unit circle and all that. And he was first known for the first works of trig.
Alright, and then we also had haylage and silo and stuff. So when we combine and cut the haylage down, we need to get it into the silo somehow. So how we do that is, this is a silo blower hooked up to a tractor. And what you do is you unload the wagon into there, and that blows the haylage up this tube right here. And so if that tube is 70 feet, we want to know the velocity of the haylage and what the acceleration was. And so what we did to get the seconds is we unloaded some haylage into there and timed it and looked to see when it came out of the top. And so to find the velocity, we took 70 feet divided by 1.243 seconds, and we got about 56.315 feet per second. And then to find the acceleration, we took the velocity divided by the time again, and that was 56.315 feet per second divided by 1.243 seconds, and we got about 45.306 feet per second squared. And then so after all of the haylage is loaded into there, you can see kind of what it goes like out into the silo with this video. Kind of distribute it through all of it, comes out that tube up there after it gets in. So yeah.
It's just like the inside of the silo where the haylage is coming in from.
And then it makes sure that it stays even throughout, so it doesn't like get all lopsided and all weird.
And then some other applications for instantaneous rate, we had economics like the production of growth and the decline and stuff, and then the speedometer. And for Riemann sums, we also had area under any type of growth or under any type of curve. And so that was like a parabola or like a rainbow. And then for rates, we did like water, the rate that water comes into a dam or through a dam.
Hey Megan,
Huh.
What did the fish say when it ran into a wall when it's swimming up the river?
Oh, damn. And then we also did angles of so like if you had a ladder and the angle that is away from the building. That's it.
That's